Hi, in this video I'm going to talk about Lipschitz continuity and the convergence of Fourier series to the function itself. In the first video I will first introduce what Lipschitz continuity is, and in the second video I will prove that Lipschitz continuity implies that the Fourier series of f will converge to f. So first recall that for all delta greater than 0, the integral from 0 to delta of absolute value of the Dirichlet kernel will diverge to infinity as n tends to infinity. Also, to study the convergence of Fourier series to the function itself, it suffices to prove that the absolute value of the integral from negative pi to pi of dnz times fx plus z minus fx tends to 0 as n tends to infinity. How can we prove it will tend to 0? To estimate the previous integral, we will put the absolute value inside the integral sign, and we will get a bigger value. However, if we do such estimation, there will be a problem. If we consider I1 and I2, where I1 is the integral from negative delta up to delta of the absolute value of dnz times the absolute value of fx plus z minus fx dz, and the second part is the integral from negative pi to pi of chi b times the absolute value of dnz times the absolute value of fx plus z minus fx, where b is the set of the closed interval negative pi to pi, taking away the open interval negative delta up to delta. Well, what is chi b? We have introduced such function before, and this is called a characteristic function. And its definition is that when x is lying inside b, then it will be equal to 1. And if x does not lie inside b, then chi bx will be equal to 0. And we know that the above integral here is equal to I1 plus I2. However, as we have mentioned that the integral from 0 to delta of dnz could tend to infinity as n tends to infinity. So it will happen that I1 will tend to infinity, and this is not the result we want to get, because we want this integral to be equal to 0 when n tends to infinity. How about I2? Well, we will show that I2 will always tends to 0 as n tends to infinity. So first of all, we write I2 in its explicit form. And remember what dnz is. Well, dnz is equal to sine n plus 1/2 z over 2 pi times sine z over 2. And therefore our I2 here can be written in this form. And if we apply the compound angle formula to sine n plus 1/2 z, we get that sine n plus 1/2 z is equal to cosine 1/2 z times nz plus sine 1/2 z cosine nz. Well, these two expressions looks familiar. We can define a function here, and this is a function multiplied with sine nz, while at the below here, this is a function times cosine nz. And what is this? Indeed, it is a Fourier coefficient of the previous function here. Well, remember that we have the Remodeler Backlemma, which states that the Fourier coefficient will tend to 0 if f is Riemann integrable. So, to show that this function is indeed a Riemann integrable function, it suffices to prove that the bottom here will not vanish. But indeed, if we restrict ourselves inside b, then we know that sine z over 2 do not vanish. And therefore, this function here is integrable. And therefore, we know that I2 will tend to 0 as n tends to infinity. So I2 is not our main focus in this study, and therefore we impose Lipschitz continuity in order to solve the problem, that is caused by I1. And we are going to introduce what Lipschitz continuity is. So let X be a point inside AB, and F is said to be Lipschitz continuous at X if there exists a delta and L such that Fy minus Fx absolute value is smaller than or equal to L times the absolute value of X minus Y for all Y inside AB such that the absolute value of Y minus X is smaller than delta. And if X lies inside closed interval AB, we know that such assumption is not necessary. And we are going to prove that we do not have to restrict our Y in the delta neighborhood of X. So here's the theorem. The theorem states that F is Lipschitz continuous at X inside AB if and only if there exists an L such that the absolute value of Fx minus Fy is smaller than or equal to L times X minus Y for all Y inside AB. And the proof, we use the property that F is integrable. If F is integrable, then it is bounded. And therefore, if the absolute value of X minus Y is smaller than delta, where delta is from the definition of the Lipschitz continuity. So, by the definition of Lipschitz continuity, we already know that there exists an L1 such that the absolute value of Fx minus Fy is smaller than or equal to L1 times X minus Y. So this is not the issue we want to solve. We want to know that if Y lies outside the delta neighborhood of X, will the same property hold? And from this observation, we know that the absolute value of X minus Y over delta is greater than or equal to 1. And if we apply the triangle inequality, we know that the absolute value of Fx minus Fy is smaller than or equal to the absolute value of Fx plus the absolute value of Fy, which is smaller than or equal to 2m, where m is the supremum of the absolute value of F, where X lies inside AB. And therefore, we get that the absolute value of Fx minus Fy should be smaller than or equal to 2m, and it is smaller than or equal to 2m over delta times the absolute value of y minus x, because we know that the absolute value of y minus x over delta should be greater than or equal to 1. So, if we choose among the maximum of 2m over delta and L1, then we can get the same inequality at the same time, even though y is outside or inside the delta neighborhood of x. So this is the end of the video about Lipschitz continuity, and in the next video I'm going to talk about how Lipschitz continuity is related to the convergence of Fourier series to the function itself. See you in the next video.